Okay, now we come towards the final panel discussion of Physics Conclave 2025. We actually had a very nice discussion in the last panel regarding one of the paradigms where one is trying to actually integrate quantum mechanics with gravity. There is also one fascinating paradigm which has emerged in the last few years where the quantum science, which happened to be one of the most fundamental theoretical understanding in the early part of 1900s, was experimentally verified and tested to a large extent, and it has now been in the realm of utility, where people are trying to utilize it for certain kind of applications. And there are also new questions which have arisen, like what we saw in the other discussions of quantum materials and advanced materials. So this particular panel discussion is about quantum science and technology. As you all know, the Department of Physics is at the core of this particular research area within the a larger umbrella of IHub. We also have many of our colleagues who are part of this panel very actively researching on topics which are relevant to quantum science and technology. It has also turned out to be an important venture, not only in terms of the interesting research questions they are trying to address, but also to push the limits towards technology and in some cases even to commercialization. And all of them actually in one way or other involved in this particular endeavor. And this panel discussion is focused towards quantum science and technology. And I'll ask our panel members to take it on.
Okay, so I'll try and keep it short. So this is overview rather than description of the results, and it's a combination of things that I do and things that I don't do, but nevertheless, maybe hopefully in some years from now I might even get down to doing this. Okay, so broadly I've kind of classified it into two parts, one relating to quantum computing, other relating to algorithmic parts of it. Okay. So broadly, whatever I do can be classified as, in some sense, part of it as analog quantum computing, meaning that you don't need the usual structure of qubits and gates to do the quantum computing part of it. So one example of that would be something like these metal insulator problems. So you have a simpler system which you can more or less realize similar phase transitions. So you look at the various properties of such phase transitions using not a typical solid, crystalline solid, but an equivalent system. So in this case, it happens to be a chaotic system, what is called the quantum kicked rotor. So there is a whole bunch of questions around which you can't easily answer with crystalline solids, but you can actually both do experiments, some of which have been done in Umakant's lab, and also you can, of course, do numerics and analytical work around it. So that is one example of what would be called a quantum simulator. And in general, such analog quantum computing is useful for many purposes, including for large class of optimization problems, and of course for quantum simulation. The other result that we recently had was related to a database search. So many of you might have heard of this algorithm called the Grover's search algorithm. Basically, if you had a large database of whatever, strings or numbers or whatever, and it's not structured in any particular way. Let's say if it is some words, and if it's already structured in an alphabetical order, it's easy to do the search. But there is no particular structure to your database, then quantum computing or quantum computing algorithm, Grover's search algorithm, says that you can do it faster than the best classical algorithm. And recently we kind of proposed a version, generalization of this Grover's search algorithm, which is called the amplitude amplification. And so that is this quantum search using quantum kicked rotor. Again, you are using a very different system. You are not using the usual IBM class of digital quantum computers for the purpose, but something that can be realized on a very different test bed. So what you see there on the left side, the figure, basically shows that the marked sites, the ones that are of interest, get amplified. So that is the usual quantum search. And then there is another class of problems which is quantum walks. So classical random walks is very old, almost more than 100 years old. Quantum walks are not exactly random, they are unitary dynamics, but they come equipped with a shift operator and a coin operator. And it's useful, and you can actually turn it into an algorithm for doing things like searching on a database. If you had a large graph database in particular, meaning it's a network of nodes and edges, and if you want to maybe search for something or reach a particular point, maybe quicker, for instance, those are the kind of things for which you can build an algorithm using this template of quantum walks. So again, so many of these are done with various students. You see the names like Bharti Kannan, Keshav is 5th year student with Rajesh, but he had done that earlier with me. So that's one part of this analog quantum computing. The other part is this quantum algorithms or quantum machine learning. So I've written a list of names here, QRAM. So RAM is something that you know, random access memory, but QRAM is what would be called the quantum version of random access memory. There are theoretical proposals for quantum random access memory for almost 10 to 11 years now, but it has not been experimentally achieved. And this QRAM is actually based on quantum walks. So one of the aims going ahead for me is to be able to come up with a better algorithm that's also implementable for QRAM. An important question with all these kinds of algorithms, so I'm not getting into details. For instance, HHL is probably one of the most important algorithms. So you can, primarily it's for solving solving a linear system. So you have n equations with n unknowns. HHL is an algorithm to go. Again, there are severe challenges in how you can actually implement it in practice on a quantum computer. So the question is about quantum advantage. All these are algorithms for which the quantum advantage is proven theoretically. It doesn't imply that when you actually start implementing it on a quantum computer, you will actually realize precisely those quantum advantages. So clearly there are many other overheads which are not accounted for, and hopefully those are the things that will inspire further work along these lines. So another important kind of paradigm that we've started working also with Mahesh and his group is this quantum reservoir computing. Again, it's a paradigm where you don't need, again, usual gates and qubits. So the idea is that you have this system of neural networks. So you remove all the neural networks and put in dynamical systems. That would be your reservoir. And for quantum reservoir computing, so the dynamical systems, dynamical elements would be quantum systems, small, simple quantum systems. You put them all together, and hopefully they would do the learning part for you. So physically what happens is you have some set of inputs that is given, and they are projected into some higher dimensional space, and then the output qubits you can simply read off and do a training part of it. The biggest advantage with respect to, let's say, the conventional neural network approach is that the training part is much more shorter. So in terms of maybe hopefully energy consumption as well as the kind of labor involved in training the neural networks, this kind of reduces that part of the expense. So here the idea was to use many of these quantum chaotic models which show very rich dynamics as elements for reservoir computing. And there are other things which currently are work in progress, like using some of these quantum chaotic models as quantum sensors, or even PDE solver, which some of us wrote proposal, but still in the works. So I'll stop at this stage and discuss more later.
Okay, so I'll try and keep it to 3-4 minutes as was asked. So my work is predominantly in quantum materials, and what I'm showing here is the part which overlaps with quantum technology, and that is the use of magnons as a potential hardware platform for quantum technology applications. Now, What is the premise? The premise is that magnons, which are quanta of spin excitations in a magnetically ordered solids, can provide a means of information transfer. And why are they important? They are important for the fact that unlike charge carriers or electrons, which are the norm in all our computing devices, magnons have a very different length scale when it comes to their transportation. So the length scale of a problem in a standard electrical conductor is the electronic mean free path. On the other hand, for a magnon, it is something called the magnon diffusion length, which intrinsically is at least a couple of orders of magnitude larger than the electronic mean free path. And so the hope is that since they scatter very differently in comparison to charged particles, you can actually have long distance information transfer when one uses magnons as a source of information transfer. Now, what are the grand problems in this area? I have listed out a few. The first, and which is something which I'm really interested in, is the quest for superfluid spin transport. So you have all heard about superconductors when it comes to electronic systems. They are at the heart of Josephson junctions, which are used extensively in quantum computing, also quantum sensing. The question is that can spins also move in a superfluid fashion, and whether one can have completely dissipation-less spin transport in magnetic solids. Now, the fact remains that some variant of this has actually been seen way back in the 60s, and that was in superfluid helium-3. Helium-3 actually has a spin, and when it becomes a superfluid, you actually have some form of superfluid spin transport, though its analog as far as solid-state devices are concerned has not yet been found till date. The other problem relates to topological magnons, and these are systems in which magnons at the surface of a magnetic solid will have a kind of topological protection, which allows, again, for dissipation-less transfer. And combining these two, one can think of a number of transformative devices which can have lots of uses in the domain of quantum technologies, for instance, the spin-Josephson junction, hybrid magnon qubits, and so on. So the reason why people are interested, for instance, in the spin-Josephson effect is twofold. One, it need not have very rigorous constraints in terms of the temperatures in which it works at. For instance, when you're looking at superconductor-based, electronic charge-based Josephson junctions, you probably know that they have to work at extremely low temperatures. On the other hand, you have a large number of magnetic solids which order well above room temperature. So even at room temperature or slightly lower than that, they are well deep within the magnetically ordered state. And so you have the potential of observing spin Josephson effects. The area of magnon or hybrid magnon qubits is even newer, whether magnons can be used as qubits, or more importantly, whether they can, in conjunction with other hardware platforms, be used for qubit readouts is a problem which a lot of people are interested in. And what our research area focus here in IISER Pune is threefold. One, it is in identifying the right kind of material systems for looking at magnonic applications. Two, it is in trying to come up with newer device architectures for magnonic devices. For instance, just last month we have a paper in the Physical Review. We also filed a patent for it, for trying to have a device architecture to measure magnon surface spin currents and to measure it using an electrical means, which could be important going ahead. And so broadly, we look at a large number of phenomena using quantum materials in which we can excite spin currents using, it could be light, it could be microwaves, it could be acoustic waves, temperature gradients, and so on, and also to manipulate them. So magnons interact weakly as compared to electronic systems, but they do interact, and that gives us the potential, the possibility of manipulating spin currents. We can look at things like parametric amplification and so on and so forth. So I will stop at this. So this is at the interface of the area of hardcore condensed matter physics and magnetism, along with, say, some form of electrical engineering. And here again, I mean engineering in a nice sense, as Srijit alluded to earlier. And so I will stop at this, and we'll move on to the next speaker so that we are still in time.
So in the morning, I briefly described what we do as a group. And I have picked up one of our interest, which also, as Srijit saying, that this session is for engineering. So I'll also say you how to engineer topological phase transition, okay, and hopefully use it in a device. So let me briefly take you that, so when it comes to quantum Hall effect, okay, so as it was mentioned that, quantum Hall effect, you have a quantized, resistivity or quantized conductivity, okay, which comes from the intrinsic topology, okay. However, this, when Srijit was mentioning in the morning, it was first observed in a Landau level-based systems, okay. However, in a material-based system, okay, the recipe to get quantum anomalous Hall in non-Landau based system is that you take a topological insulator, okay, and then you induce magnetism. That means you break the time reversal symmetry, okay. And if you break the time reversal symmetry, the Dirac cone of the topological insulator will now open up a gap, okay. So that means your Dirac electrons will now acquire a mass, okay. Now if you have a tuning parameter, the way you can like tune your Fermi level to that gap, then you have a system which is susceptible to have quantized Hall effect. So that is where you get quantum anomalous Hall insulator in a system where you have topological insulator and you have intrinsic magnetism to it. So that's what we call it magnetic topological insulator, okay, which was discovered not many years back, maybe 5-6 years back. Okay, and in this kind of system, what has experimentally observed is that, so if you put it under it very, very high magnetic field, now let's say like you take a topological insulator, you thin it down to few layer, and let's say like I have even number of layers in it, okay, 2, 4, or 6. So, and if you put it under a very, very high magnetic field, okay, it shows a quantized anomalous Hall, okay, quantized. But if you do not put that magnetic field, then you go to another very exotic quantum state, which is called axion insulator, okay. So basically, how it is tuned is that, so let's say, so if you take this bilayer, their intrinsic magnetic coupling is antiferromagnetic. Okay, so basically you have two ferromagnetic layers coupled antiferromagnetically. Okay, and if you have that kind of situation, you fall into axion insulating state. Okay, and if you somehow manage to tune this interlayer magnetism from antiferromagnetic to ferromagnetic, okay, then you fall into the regime of quantum anomalous Hall. Okay, so basically a same system can give you two quantum state. Okay, now you can make a device, okay, and if you are able to go from one state to another state easily, then you can call one as 0 and one as 1. Okay, so now that has been experimentally done through experiment. Here, where you have an axion insulating state, you have a kind of 0 Hall plateau. Okay. So this middle section, when you have no magnetic field, it is in axion insulating state, and when you have high magnetic field, it's in a quantum anomalous Hall. However, the magnetic field you require is of the order of 9 Tesla or more. Okay, so that means it's not that easy to get or access 9 Tesla magnet, and often it would require a huge energy to create that big a magnetic field. Okay, and in spintronics, one of the goal is to be energy efficient and manipulate your magnetism by electrical means. Okay, that would be much more device friendly. So what we have done after a lot of effort of almost more than 2 years, we found that we can sandwich this this magnetic topological insulator within with two 2D magnets. Okay, and due to proximity effect, okay, when this, let's say like this is a 2D magnet, spins are pointing in the z direction, that forces the first layer of topological magnetic insulator to point out in the same direction, and if you put another layer on top of it, that also fixes the spins. So that means if I sandwich my device or sandwich my topological magnetic topological insulator into 2D magnets, I get a natural coupling which is now ferromagnetic. Okay, and that ferromagnetic state, okay, gives me this is theoretical calculation that gives me quantized Hall conductivity. Okay. However, now I get one state. How can I electrically tune and go to another state without putting a magnetic field? Okay, so that's the big question. So what we do is that we, on top of this 2D magnet, we sprinkle some electrons. Okay, and how do you experimentally achieve it? You get that top surface. Okay, and you put a gate voltage such that it dopes electron into your system. Okay, and from our previous calculations, we have seen that if you dope electrons in these 2D magnets, then the magnetic anisotropy flips from perpendicular to the surface to the parallel to the surface. Okay, and when it flips to parallel to the surface, then it's no longer holding that surface in the same direction. Okay, and then the magnetism, the magnetic moment flips. Okay, so then in that case, I get an antiferromagnetic layer coupling between these two layers of magnetic topological insulators, and then I go to an axion insulating state. Okay, so basically, what we have achieved is that without putting a large magnetic field or without using any magnetic field, okay, we can access, okay, these two exotic quantum states, okay, and which can be used in a device. One of the device I can think of is called topological FET. Okay, so that is where you can use, or I think I can also use it for various other spintronic devices. Okay, so this is what I wanted to mention here.
Yeah. I am a experimental semiconductor physicist by training. Why I am saying that? Because the devices all of you are holding or writing laptops and all that are mostly semiconductors. And if we have to bring quantum technology to you in this way, my personal bias is obviously it has to happen through semiconductors. And in semiconductors, we particularly in our lab study a particular object quasi-particle which is called excitons. Excitons are nothing but bound pair of electron holes. They can be found in many semiconductors. Whenever you generate an electron from valence band to conduction band, they immediately create a hole, positively charged, electron and hole together. They immediately attract each other and form a hydrogen-like atoms. And so in a sense, I kind of try to do physics, experimental physics with atomic objects, atom-like objects moving or trapped within a semiconductor structures. And in these particular cases, we were actually dealing with a particular sample which I discussed in the yesterday in advanced material. It is a 0D 2D hybrid structure where a layer of quantum dot is near a layer of 2D materials separated by a barrier. Now, this exciton we have been interested in working on. We did work on room temperatures, but as you can understand, if the quantum device has to come at this level with mobile and laptop, it has to work at room temperature. And exciton has a big advantage compared to any other exciton and similar cousins, exciton polariton, has an advantage because the quantum degeneracy temperature below which these entities like excitons or exciton polariton goes into a macroscopic quantum state, macroscopic in a sense even a millimeter or even larger, can actually be inversely proportional to their mass. So compared to a, say for example, Umakant should forgive me, that compared to a rubidium atom which is very heavy, electron and holes are very light. As a result, you can expect exciton Bose-Einstein condensation to happen around few Kelvins temperature. Currently we are in the range of 10 to 100 Kelvin. However, based on novel materials where the excitonic binding energy is large or novel structures, you can actually think of taking that temperature where you can access, experimentally access using voltage, currents and all that, a macroscopic quantum state of many, many excitons to room temperature and beyond. And that's how many material scientists were actually interested. And yesterday we talked about some structure, advanced structures of these 0D, 2D, where we thought that we actually got the exciton BEC. Our paper was rejected by PRL, and the two most reason they rejected is that they told me that, well, if it is a BEC at certain voltages, you should be able to show that there is a periodic order and disorder that is happening. We told them that, well, excitons, electron-hole pair, they have a dipole. So because we are seeing oscillations in capacitance, which actually measures the electric polarization, collective electric polarization of these excitonic dipoles. So it is, so when the dipoles are parallel, the capacitance is more. When they are kind of random, they are less. But they said, no, you have to give us some other order and disorder presence of that to confirm it. And we now did a light emission from that same structure. As you can see, this 3D plot that it is showing, it is as a function of applied voltage, and the spectroscopy is done along the vertical axis, and the color scale is the intensity of the light that is coming out of it. So that is fine. But when we looked at it, we could see that in terms of spectroscopic width, or the FWHM of the spectra, excitonic spectra, it is also oscillating with bias. And those who does spectroscopy, they know that FWHM of any optical spectra is connected with the inhomogeneous broadening that is there. And being an excitonic spectra, we could say that there is a oscillations as a function of applied voltage of these inhomogeneous broadening or order and disorder, in a sense, the order and disorder that is coming from the populations of the excitons. And the third, and the second actually, the objection that was given to us, that we did show Rabi oscillations of that macroscopic excitonic state by varying light intensity, but they said, no, you have to come up with a time domain variation of these things. Even Mahesh also told me that if you can actually show time domain variations of these oscillations under light, then we can, it is actually much better proof. So in the last lower, rightmost lower plot, now you can see that when it is dark, meaning that square wave is the dark and light portion of that light pulse. When it is dark, there is nothing. When it is light is on, we do see long duration oscillations in that system. The second, so that kind of answers the reviewers of PRL which actually rejected that paper, and right now it is also under review. So the another very interesting part in terms of realizing these exciton-based quantum devices is that this particular 0D, 2D structure actually show fractional quantum conductance. If we plot this variation of both AC and DC quantum conductance in the units of quantum conductance, it actually shows fractional quantum conductance. It actually, usually fractional quantum conductance are kind of when you study these fractional Hall effect under huge magnetic field. But yes, we don't have a magnetic field, so it actually shows that there is a strongly correlated electron system is present. I'll just take 1 second. And also, in this excitonic system, if you actually increase the number density of the exciton, it is supposed to be, theoretically, it was shown that it can actually go over to a superconducting state of BCS-like superconducting state. So because we have in our disposal laser powers, we just hit the sample with lot of intensity, and we started seeing some splitting. I am not actually showing you all the data, but what I'm showing you is that, well, that splitting actually suddenly started at certain intensity, kind of reminiscing of some kind of a phase transition, as well as that splitting also goes down at a certain temperature around 45-50 K, whereas the actual oscillations actually stays up to 100 K. So it may be we were seeing this BC-BCS phase transition as well in this particular system. So that's what we are standing now, and we are understanding whatever we are getting.
Okay, I'll try to keep it very short. I think I showed most of the things that we do in the last yesterday's discussion. So this is just a list of things that we do under the domain of quantum technology. So the first thing is we are trying to build nodes for distributing quantum information from one physical qubit to another physical qubit by transferring quantum information from a stationary qubit onto a photon and sending it to another qubit which is physically separated. So this is useful for scaling the number of qubits in a quantum computer, essentially to build a cluster of quantum computers like you do with classical computers. So this work is underway. We are a very long way away from achieving anything in that. The second thing is we are halfway through building an optical atomic clock, which I told you yesterday, using an extremely narrow optical transition in strontium, which will be useful for not only building a very stable clock, but also will be useful for doing fundamental studies. The third one is on using atom interferometry, replacing light with matter waves to do many things. And one of the things that we have demonstrated is to build a gravimeter, which is essentially a Mach-Zehnder interferometer of wave packet which is falling under gravity. And there, because our system was not, the lab system is not designed to actually push the sensitivity, we have gone up to something like a 6th decimal place in the measurement of G. But we are building a new system which is specifically going to be designed for being low noise system, where we target to improve it beyond like 8th decimal place. And moreover, we are also working on implementing squeezing of momentum states to reduce the noise in one of the variables. So in this case, it would be the number of atoms and phase of the interfering wave packets, which are the conjugate variables. So we'll use principles and some of the ideas on spin squeezing to reduce the noise in one of the variables that is going to be measured in this interferometry to increase the sensitivity even further. And the last one there is on building a gate-based quantum computer using ions as qubits, and that work is also underway. So as I said, all these four projects are being implemented using 3 types of atoms. Okay, one of them is in an ionized state, and the others are neutral atoms. So that's about it. So, yeah.
I am a lazy person, so I have not changed the slides. And I also, I said many things yesterday. In the interest of time, I just leave the slide as it is, and we can move on with the next part.
Yeah, actually, because of the fact that there's 15 minutes, we can actually utilize to have question answer sessions, because I can see already many hands are popping up, and you guys will be bombarded. Get ready.
Hi, sir. Sir, so my question is a bit application-based in the sense that I saw a paper outside by a few of Dr. Santram's students on how they were able to essentially forecast a simple time series by using kickback. And my question was, how do these algorithms and other quantum machine learning algorithms compare in complexity to the best traditional algorithms that do for time series analysis? And one coupled question with that is, these algorithms are still in a sense probabilistic. So there will be some uncertainty. And if I have more parameters in a system, essentially like a financial time series or like a geological time series, these parameters will simply multiply and the uncertainty will go haywire. So it leaves room for, it does not leave room for like the catastrophic examples. Like there could still be a probability of having catastrophic results, which is dealt with deterministic but cannot be dealt with like more probabilistic algorithms.
Okay, I think the first part of question is about comparison with classical time series prediction techniques. Okay, I think the frank answer is as yet the complexity analysis of these kinds of algorithms are not yet done. So we do not know for sure whether it is advantageous or not, but the hope is that especially if you are going to deal with maybe larger amounts of data, hopefully this could be in terms of complexity better than typical time series analysis techniques coming from, let's say, power series and all the stochastic processes. And the second part of the question was about adding more parameters. See, I don't know. So I think you said something like adding more parameters will make it go haywire or something like that. So in general, I think if you keep adding more parameters, first of all, the complexity of your algorithm itself is going to get much harder. You need to determine all the values of those parameters. So it's a huge optimization problem. So that it just makes it more harder. But on the other hand, if you throw in more and more parameters, I think it's less likely to go haywire. So you will kind of fit the training data very well. So whether it would actually do a better job when an unknown data comes or not, irrespective of how it works, but would do a very good job with the training data. So it's unlikely to do bad.
I have a question for Dr. Nair. You were talking about magnons for information theory, and there's a poster outside about sensing and magnons using FMR. You also mentioned that they can be sensed with electromagnetic excitations, such as light. Could you talk a little more about how we can sense them using optical techniques, and like, what's the drawbacks and advantages of electrical or optical readout?
Okay. So
that makes sense.
So what I said was that it could be excited using electromagnetic means, but they can also be sensed using electromagnetic means. So when you're talking about spin currents in solids, the way the easiest way of doing an optical measurement of that is to look at the magnetic contrast, which is a technique similar to, say, magneto-optical current and so on. As far as potential applications are concerned, it is a little less preferred. The reason being that when it comes to devices, one would ideally want to read out currents or voltages. It makes it also easier to integrate with existing platforms. So there, what one does is to use an effect known as the inverse spin Hall effect, which basically then can convert a spin current to a charge current with some efficiency, which is not terribly great at this point, but nevertheless it does the job. And in that way, one can, read out a voltage which corresponds to a spin current, and that is what is the preferred modality at this point of time. Does that answer your question?
Sir, my question is to Mukul sir. Sir, you have told that, sir, like we have MTJs available. So how this topological insulators are registers are better than that?
Say it again. I just was trying to.
Like we have MTJs available, magnetic tunneling junctions.
Yeah.
So how this topological register are better than that?
So what I showed you here, I do not completely understand your question, but like what I meant to say here that like you can utilize two exotic quantum states, okay, and if you can in a single device, okay, if you get two quantum state in two different devices, okay, that doesn't help me, okay, or maybe partially help. But if I can get two different quantum state in a same device, okay, then basically I can tell one of the state as 0, one of the state state 1, okay, and that I can also do by means of electrical field without getting away with completely with the magnetic field.
Yeah, magnetic
Okay.
tunneling we need magnetic fields.
So here it is completely done with electrical field, and maybe the back of the envelope calculation, what I see is that if you have a high dielectric oxide gate material, then the voltage probably you would be requiring of the order of 10 volts or so. So that's probably very easy for experimentalists to handle. Yeah.
Hi. So my question is regarding this electron doping that you talked about to get the different state in the topological insulator. So how do you exactly plan to control the system with that? So you explained how we get the two different states, but since we need an exact control in between those states, so do you control how the doping of electron you're doing? Like, do you have a control over that?
Yeah, it's basically when you dope electrons,
right,
the way. So in my theoretical calculation, I only talk about electrons and holes. If you want to mimic that in experimentally, how will you do is that by getting it. Okay, so you have a top layer, okay,
right,
and you gate the top layer,
okay,
put a bias voltage,
okay,
and that bias voltage I was mentioning that of the order of 10 voltage. Okay, so if you put a 10 voltage bias, it would dope enough electrons into the system to flip your magnetic orientation.
Okay.
And once it flips the magnetic orientation, which is not an active device part, it manipulates or engineers the magnetic interaction of your active device, which is magnetic topological insulator.
Okay.
And you go from one state to another state.
Right. So also, this one more question. So this that you explained, it is a device that is mimicking only one qubit, as I understand it.
No.
Right.
If you are in axion insulating state,
right,
it is one bit.
Huh.
Okay, one of the bits.
Yes.
Let's say 0.
Yeah.
And if you are at a quantized 1, okay,
yes,
then it's another bit.
So in total, it is just one qubit, right?
0 or 1.
All right.
2 qubits. 2 bits, not qubits.
Hi, I have a short question. Yesterday, Professor Rapol kind of ranked this various architectures based on scalability. So I wanted to know that after this recent announcement of this topological qubits by Microsoft, Majorana 1, what do you think about the scalability in that? And I have just a small second question, that if we achieve scalability, then the number of parameters of the quantum space increases exponentially, and doing quantum control on that very high dimensional space is also a very non-trivial task. So that, I think, is also as challenging, if not more, as scalability as one of the criteria. So I just want to know your opinion on that.
See, talking about scalability in general terms is what is scalability? You want to increase the number of qubits as many as possible. Now, in terms of, if you talk about different platforms where the bottlenecks are, they are at different levels, there are different types of bottlenecks. I'll come to the recent one, the Microsoft's one soon, but before that, one should understand what scalability, what are the problems involved in scalability and what it means to all this. So you have many platforms, right? I mean, you have superconducting Josephson junctions, you have the atoms, ions, and there are spin qubits also now. So you create islands of localized spins in a 2D electron gas. The problem is, in case of atoms, there is no issue in increasing the number of qubits that you want. But then you have other problems. I mean, once you have so many of them, how do you read them, how do you address them, and then there are global effects of decoherence and all these problems. Now, in case of superconducting qubits, imagine you have 1 million superconducting qubits. You can obviously fabricate them on a chip. But then the problem is, how can you send million RF lines going into the dilution refrigeration, right? So it's a different level of problem. So there are different kinds of problems as you increase the number of qubits. And on top of that, you have this problem of decoherence. And obviously, nobody talks about what happens if I have a few tens of millions of qubits, right? See, there is going to be a classical, quantum to classical crossover at some point. That one has to deal with. I mean, there are going to be then emergent phenomena. It's not that each of these qubits are going to behave individually like you want. Either you want, I mean, it may all behave like a single solid state object which has already, 10 to the power 23, 24 but number of qubits
sorry
automatically.
to interrupt. I think we don't need millions of qubits.
No, I'm saying some people keep talking about having so many qubits to do a practical implementation, right? So nobody actually knows how many qubits they want. They just keep throwing
If we have
numbers.
1,000 qubits, logical qubits, I think we can do certain things which are beyond the capacity of supercomputers.
Yeah,
right?
but if you look at the roadmaps of some of these big guys who are creating a lot of noise and keeping this game going, you have that, like, for example, you would have seen the roadmaps of IBM and all, right? They show like non-exponential increase in number of qubits. But, okay, I'll just finish the last part about the Microsoft. I think even if they succeed in showing a qubit based upon this topological qubit, whatever it is, Majorana, fermion, or whatever it is, that will also run into same problems as what superconducting qubits are going to run into. But only advantage that people are looking forward to in this topological qubits are, they are prone to be less immune to the environmental fluctuations. So the error rates are going to be much smaller than them. They are not going to be zero, but they are going to be much smaller than what you have with other qubits. Yeah, please.
Yeah, so in this situation, I think if these excitonic based quantum computers can be realized, because all the excitons are being driven to the ground state of that BEC, so you basically have identical excitons sitting at the same quantum state, and you possibly have many qubits which is there, and you can address them not only using bias but also using light. So I feel that these kind of challenges can easily be addressed in a semiconductor-based excitonic system.
Prashanjit.
Yeah, so I have a simple question probably for Santanam. So when we talk about fitting something to a data set, right? So, I mean, even if I do a simple fitting, the more number of polynomials, the higher the order are, more is the parameters. I can fit anything basically in principle. But then at the end of the day, you do end up in doing overfitting and meaningless fitting. So in that context, for the quantum algorithms, in context to his question also, so how do you, address these things, or, are there your thoughts, or, yeah?
See, I expect that all these problems will remain, overfitting, underfitting and all that. And say right now it is at a stage where you first want to demonstrate that the idea works. You know, whether if you're using, say, quantum reservoir computing or any such paradigm, you first want to show that in principle it works. And then you need to worry about these very finer issues about overfitting and things like that. And I think similar issues would remain, yes.
Yeah, because you said that more parameters will be there.
Yeah, that's it. See, more parameters would mean overfitting. Yeah, that is bound to be there, yes.
Yeah, Sachin has
Thanks.
a question.
About the quantum algorithm, so I understand that it's because of maybe Grover's algorithm that dealing with larger data, it will be easier to do with the quantum, I suppose. So what is, because as was discussed that nothing is just the closed system, right? Everything is open system. So is the quantum algorithm understood if there's a decoherence, and then how does it get modified? How far it can has advantage, like how much decoherence is okay, you know, that kind of limiting thing is understood?
Yeah, there are some calculations. I think, if the fidelities can be more than 4 nines, 0.9999, so then there is a calculation that says that error correction algorithms work, and there is a threshold for error correction to work, and then so you can do error correction and get rid of errors and so on. But that comes with a extra cost, that you need more resource in terms of number of qubits, because one logical qubit consists of 5 qubits or 9 qubits, and together they form one logical qubit. Having said that, there are two issues. There is a physics issue and there is an engineering issue. So recently there was one talk by Google chief engineer of quantum computing. He was saying that physics issues are all solved. So as what he meant was, there is no fundamental blockade in terms of physics. It's only engineering issue now. So that's you have to find better materials. You have to suppress noise and all that. So there is no. It appears that there is no fundamental physics blockade. You want to?
But there are, I think, a few other overheads which are generally not accounted for in the algorithm. When they say, like, Grover's algorithm is quadratically faster than this thing. For instance, you need to take your data and convert it into quantum states. So the assumption is that somehow it can be done in maybe linear time or something like that. But those are not accounted as part of the algorithmic cost. So I think when all that is taken into account, it's not clear whether there would be any advantage left and so on. I think they are still work in progress.
Okay, so on no uncertainty, we will finish this particular panel discussion. Thank you all for a very nice discussion, and we also actually come towards the end of the conclave. But we also actually need to mention...
Before Pawan closes, I want to thank Pawan and the team of all the students.
No, in fact, there is a small formality. In fact, if you guys can get on, I want all the volunteers to be up there. Come, please, sir. Please. Everybody, each and everybody who has been part of the volunteer team, I request you all to come up on the stage. I think as we speak, maybe some of them actually are also doing still some work in the background. So quickly tell your names and what you people do at IISER. Just quickly, press it on. Quick.
I'm Dharya. I was photographing here, and otherwise I generally work in Ashish's lab.
Hello, I'm Gautam. I'm a PhD, second year. I'm working with Ashish, and here I was taking care of mics and everything.
I'm Vivek. I work in Professor Mahesh's lab. So I was taking care of hall arrangement and the poster.
I'm Anupam. I'm working under Professor Regis Nath. I'm taking care of food department.
I am Pawan. I am working with Atkur sir. I am taking care of food division.
Hello, I'm Prachu. I work with Saurabh Dubey in experimental high energy physics, and I'm handling the website and social media.
I'm Sneha, second year PhD student. I'm in the poster and hall section.
I'm Shweta, working with Dr. Atikur Rahman, and I distributed merchandise with 2 other people.
I'm Avinash. I'm working with Dr. Atikur Rahman, and I was in merchandise section and in food section.
My name is Subham Padi. I'm working under Professor Shiv Prasad Patil, and I was in hall and merchandise section.
Myself, Sri Krishna. I am working with Professor Shiv Prasad Patil, and I did help in printing the merchandise and to organize the food.
Myself is Vedant. I am working with Professor Shiv Prasad Patil. I am in poster session and hall management.
Hello, my name is Shagun, and I am working with Professor Surjit Singh, and I am in poster and hall management.
Hello, myself is Pankaj Gupta, and I was coordinating with hall management and poster session along with my all hard-working volunteers. Thanks to them. And I work with Professor Surjit Singh also.
Hi, my name is Joel. I'm in Umakant Sir's lab, and I was in the merchandise division.
Hi all, I'm Yash. I was heading the food department.
Hello, I am Umasankar and I am supporting yes. I was not the part of the team earlier.
Hello, I am Azad and I work with Dr. Asna Bajpayee. I am handling the food management.
Hello, I am Meghasri working with Dr. Atikur Rahman, and I am in the poster and hall management.
Hello everyone, I am working with Dr. Atikur Rahman and my name is Manisha. I help with poster arrangement.
Myself, Vaibhav. I am working with Dr. Aparna. I was involved in poster session and hall management.
Hello, I am Shobna. I am working with Professor Rajesh Nath. I helped in sticking posters all around the campus and photography.
Hello, my name is Meghna. I am working under Surjit Singh Sir's lab. I am in the club of social media, taking photography.
A big round of applause to everybody. Thanks a lot. It would have been impossible for us to pull this through without the excellent support by all these research students in physics department. They have really put a lot of time, effort, and joy in bringing this very well. Thank you very much. Thanks a lot. Thanks a lot, folks. Thank you. Thanks a lot. Yeah? Thank you. Thank you. Okay, some small formalities. Before I hand over to Mahesh, let me actually re-emphasize the fact that all these things would have not been possible but for the excellent support from all the faculty members in the physics department who actually have been very supportive about not only just showing up but also realizing this idea. This is a very different kind of format we tried, and everybody were really supportive of this particular thing what we tried to do. There would have been maybe small minor errors. That is me, okay? And everything which is good is because of the students. So thank you very much, and hopefully you all had a good time. Thank you.
Okay, just one more minute. So this was entirely handled by this volunteers, of course, and also this committee of events and outreach, or outreach and events. Okay, so this committee is just, I think, 1.5 months old. I think it is younger than Donald Trump's cabinet. Yeah. 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 So, yeah, and they have handled it, very meticulously, in a very meticulous and in an excellent way. There is one danger, though, that Pawan thought it's a one-time job. I think now I think people are asking it to be annual event, and we'll see. Yeah. Yeah. Right. Right. Yeah. I want to thank everyone, as well as I want to thank the support of Dean R&D as well as the director. Director wanted to be with us today, but he's out of station. Anyway, thanks to both Dean R&D and director. Thank you, everyone, and hope we'll have this session again. Pawan promised food yesterday. I think we had lots of food, both for thought as well as for stomach. I think one more is due now. So we'll all head towards that, right?
Yeah.
Okay. Okay. Bye. Thank you.
So, thank you, Mahesh. Thank you very much. In fact, I would also want to mention that the most important thing is, the origins of the idea and other things really goes back to some of the things what our committee, I have to explicitly mention. I wanted to be also the last thing I want to mention. A big round of applause to Ushashi, who really played a very critical role. Deepti Moy is already gone to take care of his daughter. He's going to be back with us later on. And also Ashish and Surabhi are not here, but they also played a critical role. There's a lot of planning behind this kind of methods what we have used, and there's a lot of footwork which actually has been done by a lot of students. Okay, I again thank all of you for being around. Yeah.
I forgot to mention, big thanks to auditorium staff who have been, yeah. Thanks Sunil for remembering.
One more thing is also, physics office, they also played a critical role. Prabhakar and all his team, they were very, very supportive. And so as you know, all things have to come to an end. So this is just a beginning as we speak. The outreach committee would also do a little bit more outreach towards, bringing physics to a larger audience. We would want to also get a lot of support from our physics students, whomsoever is interested. We will actually write to you at some point of time and request your cooperation in that. Okay.
Also thanks to media.
Yeah, thanks to Science Media Center. They have been fundamental to record a lot of stuff what we have here. At some point of time, with all the editing, it was not live stream. And you can see there is a good reason. In-person events actually have still a lot of value. And second thing is also, of course, this is a technical sessions, and some people might want to edit it properly and also put it out. Hopefully, it's going to happen subsequently. And once it's there, forward karo. Okay? And this is all very critical for our department. So thank you all. Thanks a lot. And have a nice weekend.